All right, so we want to talk about the gamma function, but we're going to do something special today. We're going to view it in a way, at least that's novel to me, and it isn't what you run into if your search for the gamma function is included, say, Wolfram Alpha or Wikipedia, and no other visual generator. So we're going to be viewing the phase diagram, or the phase plot of the gamma function from giant scale and zoom all the way in. And you're going to see some fantastic structure. Before we do, I want to review some of the interesting features and facts that we know about the gamma function. First of all, in general, what is the gamma function?
It partitions things.
It's the analytically continued version of?
From the zeta.
From the?
Oh, the factorial.
The factorial function. Okay, so the factorial function is defined for n's that are whole numbers, right? N equals 1, 2, 3, 4. And so really, if you were to draw it as a function, its output, it gives you answers that are on the real number line, right? But nothing between. It's just dot, 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 okay, for the answers.
The gamma function is a formula along with factorial.
So the gamma function is a way to analytically continue that structure through the whole plane.
You could think of it, it's also like a measure of growth and or decay, depending on, because it always usually shows something either growing or decaying.
Yeah, okay. It's totally directly related. All right, the gamma function is also directly related to a very famous thing in the zeta in mathematics, the zeta function, right? It's the same conversation. In fact, the zeta function is kind of a double copy of the gamma function, by which I mean, let's see, which one should we start with? So the gamma function, if I say of s, here I mean s equals x plus iy, just a two-dimensional number, okay, shorthand for it. Then I can write it in terms of an integral, 0 to infinity, x to the s minus 1 over e to the x dx. Okay, and the super famous zeta function can also be written in terms of the gamma function. 1 over gamma s times by integral 0 to infinity x to the s minus 1 over e to the x minus 1. Other than this minus 1, this would be that. This would be 1 over the gamma function times by the gamma function, which equals 1. Okay? The whole thing would just be 1 if this 1 wasn't there. All right, so really it's kind of a double copy of the gamma function with an offset. Okay? All right, but the zeta function, of course, is the one whose zeros are directly related to all the primes, right? There's a lot of central questions that people famously know about the zeta function. Okay, so we want to focus more on the gamma functions, like maybe a simpler version to start with, right? Okay, so what are some cool features we know so far about the gamma function? Anybody remember any of them?
Well, gamma 5 is 24.
Yes. Remember, it's one specific one, gamma of 5 equals 24. Okay. What about...
Gamma 1 over 5 is peak algorithmic incompressible.
1 over negative 1.
I don't know.
0. In fact, 1 over gamma of negative n equals 0.
Anything negative?
Yeah, well, n is 0, 1, 2, 3, 4, 5, 6. So, very specifically just those. Well, all the way up. But the zeta function, by the way, has an interesting corollary. Starting with n equals 1, not at 0. So, offset in the start. But look at the interesting negative n, negative 2n. This one's inverted.
Oh.
Okay, and that's defined in all of its trivial zeros, all the ones that go off to the left, right? That are trivial because it's easy to expect or talk about the pattern that captures all of them. Okay, so here's another one. Let's see, gamma of, not zeta gamma. I could have done some zeta, but we don't need to. Gamma of 1/2, negative 1/2. They're kind of interesting. Remember this one? Square root of pi. Okay, that seems kind of interesting. So the gamma function is, for us, interpreting the connectivity in the number line or in the field as a hyperbolic construction. So it's central for us in describing how the construction in numbers exists to begin with. At least that's where we're going. So this square root of pi is extremely interesting. Let's just change this to gamma of negative 1/2. What would you expect that's going to change?
Is it going to be pi?
Negative square root of 4 pi.
Oh.
So if you multiply them together, you get negative 2 pi.
So, but let's see. So,
Oh.
well,
Here's another beautiful one. Gamma of 3/2 and gamma of negative 3/2.
Let me go out on a limb and say it's probably 3 different things. I'm going to go with a Lemniscate for 500.
That's probably a good guess to go with. It's actually square root of pi over 4.
Okay.
Okay, but the other one,
Oh, that's interesting.
Okay, so these are just single inputs and their outputs, but having a geometric output makes the story become a lot more interesting, at least a lot more details to follow, suggesting that the story is much more interesting that we're after, right? So most, I would expect, have been introduced to like a unit circle equation that's in terms of cosine squared and sine squared, right? So we break it up in terms of the unit circle up in terms of cosines and sines, like, you know, and we're very familiar talking about this simple wave because it's like the unit wave, right? What do I mean? It's amplitude, its height up here is 1. Its maximum dip down there is -1, right? It's the unit size this way. And then this way, what's the distance in x? Like, what do we call this point?
Well, that would be 2.
2 pi. Yeah. This is the 2 pi, because it's the first time we've closed the circle. So 1 period, right? And then we're going to repeat, repeat, repeat. Okay, or we could start up here in our phase and do the same thing. But in either case, we have the feature of 1, 2 pi built in, even pi, right? There's a fixed unit in here that we care about too. This one's right at pi. But there's another feature that's built in that is extremely important. So we're probably less familiar with it. This one, this length here, right? That's a specific length. If you take that, if you put a string there, exactly on there, and then you straightened it out, it would have an actual value, an exact fixed value for this curve that we always talk about. What is the value? Okay, I'll call it the length, the arc length of the sine wave, which is going to be equal to the arc length of the cosine wave, right? So, and it turns out that that's equal to 4 pi divided by the Lemniscate arc length plus the Lemniscate arc length. It's not a very good S. Okay, this Lemniscate arc length, let's go back to it. There's 4 Lemniscate constants, S, L, L1, and L2. And when we draw in the Lemniscate of Bernoulli with equation x squared plus y squared squared equals x squared minus y squared. So this point is -1, this point is 1. The arc length of that curve is S. L is one petal, the length of one petal of the curve. So it's S divided by 2. L1 is the length of 1/4 of the whole thing, or 1/2 of one petal. Right? So just from here to there. That's L1. And L2, I think, is pi over S. And make sure. Yes. Okay, but I can write these 4 Lemniscate constants all in terms of there, pi over S over here, because I want to write all of these now in terms of the gamma function. Okay, so the first one, actually I'm going to need more space. So the first one, S, equals gamma squared of 1/2 squared, or 1/4. Okay, our argument of 1/4 is a familiar one in our hyperbolic construction, over square root of 2 pi. Beautiful, but this is an answer. This is an exact answer to what the arc length of the sine wave is, right? This value is required for the answer. Okay, so L, can you guess? Cool.
What's exactly half of the Lemniscate?
Half of this one?
No, like in the actual graph. What
Oh.
point is exactly half of the Lemniscate?
This is the full length. So half the length is starting from the middle and you're doing one petal.
Yeah, it's recursive.
Okay.
When you come back to 0, you have achieved a half.
Well, at the crossover point, wherever it is.
Yeah.
And then the last one, of 1/2 over squared 1/4. There. There's the 4 Lemniscate constants in terms of the gamma function. So this gamma function is intrinsically important to how hyperbolic structure fits together, pulls apart. Right? It's built in over and over and over in its features.
I mean, that's very interesting, just because, like, if we're going to make the claim that we're utilizing a model that is partitioning spherical forms, this seems to, I don't know, maybe have some relation to the partitioning of spherical forms.
Yeah. It is related to, let's see, volume of an n-dimensional hypersphere is equal to pi to the n over 2 over gamma of n over 2 plus 1. So yes, intrinsically related. This is the volume of an n-dimensional hypersphere. Like, you want a 12-dimensional one, put 12 in for n, okay? 12 in there, 12 in there, and then this will calculate the volume for it, for that higher dimensional sphere. If you want the surface area of, say, an surface area for n minus 1, 2 pi n over 2. Oh, I should have put r to the n here. Sorry. R to the n minus 1. Okay. Sorry, I missed that before. So, yeah, it depends on r also, but I didn't have an r in there. So there we go. So surface area and volume of an n-dimensional hypersphere is calculated this way. It's fixed this way for every dimension of hypersphere. Okay, so it's, yes, it's directly related to how a sphere decomposes.
For a given radius, you can just plug that in for n dimensions and I'll calculate it.
Yeah.
Cool.
Yep. Okay. Here's another cool one. If you take a series, if we take the limit as n goes to infinity, pi to the 0 over gamma of 1 plus pi to the 1 of gamma 2 plus pi to the 2 over gamma 3 and so on. Okay, so now we're taking the volume, this translates to taking the volume of all the even dimensional hyperspheres. We're taking the volume sum of all the even dimensional hyperspheres, and it comes out to being e to the pi. It's really beautiful, really beautiful. Here's another thing to say why. E to the pi itself has a relationship directly with this one, with S, with our whole lemniscate arc length, right? The one that's also related to the arc length in the sine. Okay, what is it? S to the 8 times the Weierstrass constant to the 8 over 8 squared. This is the simplest fractal, right? This is the constant representing the simplest fractal. This is the constant representing the arc length of the unitary lemniscate. Okay. All right, so lots of beautiful connections in mathematics, a lot of beautiful connections in number theory and so on. But the goal is to get more intuitive sense. So these are like the breadcrumbs. These are the treasures you find along the way that tell you some sort of logic that's built into reality. This is even just built into regular circles. So to really understand you've decomposed this into cosines and sines, you need to know this feature now. This feature depends on lemniscates. You need to understand lemniscates to even tear apart circles, right? To really deeply and richly get what's happening when you tear apart circles, I should say. Okay, what we want to do now is look at the gamma functions. So a normal way to start the investigation to look into the gamma function, right, is to go to Wolfram Alpha and just say maybe plot gamma of x. Right? This is a good introductory starting place. And then you might want to zoom out, get some different scale, like x from negative 100 to 100, and see how different it looks when you zoom out. You see, ooh, wow, now it's like a straight up wall, right? It's hard to interpret much other than I have a wall there. Let me zoom back a bit. Just go from negative 10 to 10. So it's definitely got some character in it that's really steep and therefore difficult for humans to parse, right? Maybe a logarithmic way of looking at it might be easier. It's maybe a hint, but when we're zoomed in near the center, around 0, right, you can tell there's actually some structure that's kind of interesting, especially on the left-hand side. There's some repeating structure up and down, I think, right? If you think of these things in terms of twisted animal balloons, it kind of starts to help. There's a whole bunch of repeating pieces. Yeah. All right, but we want to maybe look in a more interesting, or I'm going to zoom in again, go from negative 1 to 1. We want to look more richly into the functions. So we want to extend our argument to make it two-dimensional. So instead of x, let's just say x plus iy. So now it's a complex number. Now I didn't have to tell it what range to put for y. It's assuming it's mirroring the range. Okay, you can stipulate if you want. But still, at the same range, now look how much richer the picture got. Right? There's a lot more going on, a lot more to investigate here. Okay, now this is called a surface plot. This is one of the genius moves that Wolfram gave us, right? This gives us a way to easily just take a function, throw it in here, look at the surface plot. Surface plots can be torn apart into the real and imaginary parts, so you can compare those parts. You can start to get a feel for what real and imaginary parts do to each other, what they are doing with each other. Right, because they come together. All right, so this is a much richer form. We can also now zoom out and see how much different this is. Oh, we get a lot more structure, right? We zoom out 10 by 1 power, and we get a lot more structure. Now it looks like it's a flat sheet on one side that gets twisted up just right magically into this really beautiful symmetric form, right? Looking straight down, you can see the divisions, all this twisting pattern. You can totally see the twisting lines. Right? There's a lot of structure happening in here, but you can get familiar with it. I'm going to go out 1 more power just for symmetry. I mean, you can go out as far as you want and take a look. It starts to get crazy, right? And yeah, it's already crazy. It's like, how am I interpreting this now? It's a wild, it looks like a mosaic, like I could turn this into a carpet or something. It's a beautiful pattern, but what's going on? Okay. One way you could try to tell what's going on is do this by changing your scale, tiny step at a time, right, and slowly watch it go. Or another way is to take a different kind of plot of the gamma function. Oh wait, before we get to that step, there's one other way to look at the same thing. Let me zoom back in to, say, scale from -5 to 5. Okay. Here's our familiar inside piece, this beautiful little shape, right? Now, I can also try to plot this structure from inside out, meaning I take the argument and I just divide it under 1. So 1 divided by the argument. So now let's just put that in there. 1 over, make sure to keep parentheses good. And this is another way to look at the gamma function, right? Wow, something completely different happened. That makes me want to zoom in. Let's zoom in. I'll start from 1 and -1. Wow. This is a different story, right? It's almost a weaving story instead of a division story. It's beautiful, right? Let's go divide by 10. I'm going to zoom in and power 10 here. Yeah, wow. I see a lot more features here, right? But now both of these stories are stories that help us put together what's happening in here. I see some shape happening on the inside too. Almost like a heart down there and a circle, almost a circle in the middle. Anyway, so this is maybe a method that somebody who's interested in understanding the gamma function might use, right? To look into it. And it's a fantastic one that I recommend. Another way is to look instead of looking at the surface plot, we could look at the phase plot. So we could ask the computer to assign to every pixel what its phase is, color it by its phase. So we're going to just take a range of the rainbow colors and go from 0 phase all the way back around, right? And just assign them to a color. And in this way, we're not looking at the surface now. We're kind of looking, you could think of it as almost as a derivative map in a way, right? You're looking at what the surface is going to do, where it's going. You could also think, well, if this thing is a field, maybe, then the color of the field tells you the direction of each pixel, right? Okay. The next step was just to code. Here, put it into PyCharm. This code just for the gamma function. And you see that we put in a complex argument, x plus iy. Okay, this is the way we write that there. And then we just make the frames, but we logarithmically zoom in so that we can see what the phase of the gamma function looks like as we zoom. And what we find is this. Keep going. A lot. Oh, let's start over a little bit. We got to say little things about this. We start at the beginning here, and it looks kind of like noise.
A lot like noise.
Right? I mean, you might see, when you stare at it for a while, I see that there's definitely a little more red on the left, more blue on the right. And that's pretty much all I can say. The rest is noise. All right, and we start, and we kind of see some little structure showing up. There's a structure of a certain size,
Yeah.
right? And it's getting a little bit bigger now as we zoom in, and you see a lot of structure suddenly appear and wind around. And you can see things getting bigger. Yeah, it's a lot of beautiful, beautiful structure. Now, what is this structure telling us, or what is it relating to? This is the phase plot of the gamma function as we zoom in from like 7 orders of magnitude all the way down, okay? And as we do, when we get all the way down, it turns into this simple 3-prong modular form. Very simple. A different rotation speed this way than that way, right? Fantastic and beautiful. Okay, there's another phase plot we can make, remember? We can turn the argument upside down. So we can do the exact same thing, use the exact same codes, but 1 over parentheses x plus iy, okay? And when we do that, we get this one, which I find to be absolutely beautiful. First of all, let's look before we start. Off to the left, we have the phase, it's all 0 at red, okay? And we have a branch cut right down the middle of red. Branch cuts are always in red, if you notice, okay? But it's coming from negative infinity right into, zooming in towards 0 there, but stops before 0, okay? And it also crosses this circle that's a branch cut. So let's zoom in to the, keep track of the branch cuts and the inversions around them, but ooh, now we get 2 lobes versus 1 lobe. 2 lobes, 1, 2 lobes, 1, 2, back and forth. And it's highly ordered and striped on the edges right now, but then it becomes tending toward that chaos look again. Beautiful, isn't it?
It looks so different, but then it ends the way the other one starts.
Yeah. Yeah. Okay, so this is something I just wanted to share. So, you know, the code's pretty easy to extend. In fact, I'll probably make an extended video to show what the sine and cosine and tangent look like in terms of phase, right? And the hyperbolic sine and hyperbolic cosine and so on, right? So a bunch of functions we can graph and view this way. And I'm not claiming that we're the first ones to be doing it. It's not novel. This is just now new to me, and I'm excited about it, so I really want to share. It's a beautiful way to look into functions that we may feel like we're really familiar with. And so we can point out that all along there's a feature there that we hadn't really pinned down. We hadn't really made sense of yet. This gives us a picture of that story, right? The sine and cosine, hyperbolic sine and cosine. This is all the actions that we're talking about here. Literally the actions we're talking about with E. Anyway, this is a beautiful look into the construction of numbers, a beautiful look into number theory, or you know, the beautiful patterns that we found in mathematics or in algebraic geometry. In fact, to make that clear, so these numbers are famously irrational, right? Pi is famously irrational. So what's the thing with irrationals? Irrationals don't really have a lot of equations. Rationals have a lot of equations that give you another rational. So if you add together any 2 rationals, pick your favorite 2, right? It can be a fraction or a whole number, whatever. Add them together, you're going to get another fraction or whole number. Right? That's the output's always going to be something that has a name. Before you did the operation, there was a thing that existed already that had a name. But when you pick, I don't know, e plus pi, these are 2 irrational numbers, you can't write meaningfully q. There is no other q that is equal to e plus pi unless you're just making it up right now. So I'm making that combination. There's no other way to get there naturally, though. Okay, so in most cases, irrational numbers don't have simple form equations like this. So when they do, it's really interesting. And here, there's a whole bunch of them. Irrational numbers that have simple form equations, they're literally equal to other things that are irrational, right? There's other irrational numbers in there that they have equality signs with. Anyway, all that structure is really fantastic to discover and observe. But I think fundamentally it's important to keep the reason for why, because this, we think, is unveiling the actual structure that's maintaining the logic of our reality, right? That's keeping the code of physics, that's keeping the rules in place as they are, but also the division actions and sizes of actions. So all the different constants in nature are all being built in by this geometry, by these constants, the geometry that's using exactly these constants. So the more we learn and get familiar with, well, on any intuitive level, the more we get to digest what these constants of geometry are, and the more we can digest what the constants of physics are, right? The more we're understanding reality on a deep level, meaning it's like learning a new word, or even more powerfully, learning about a new concept, a concept you'd never conceived before that all of a sudden connects other concepts you'd heard of. It's something, this miracle thing, you've heard of pi before, all right? Another magical property of pi in relation to the gamma function is it makes the lemniscate constant, right? So anyway, this is what we're doing here at the physics monastery. And it's beautiful and fun just to absorb or get to point our cognition towards these mysteries in a new way, like to get to view a visual that's telling you something about a modular form like this. So just wanted to share, and I think that'll be it right now.
Cool. That's pretty fantastic.